Hello and welcome to helpyourmath.com. In this video, we're going to go into a little more detail about the tree diagram. So in a previous video, I did discuss tree diagrams. They're one way of representing all possible combinations. Previously, we talked about one-part and two-part tasks and different ways to represent those. Unfortunately, if we get to three-part tasks or more, we can't use those methods. So we can't use a product table. Listing can be very challenging. So one way we can organize all of the possible results is to use something called a tree diagram. Tree diagrams can be displayed in one of two ways. We can display them vertically or horizontally. More commonly, we use the horizontal approach. And tree diagrams are not only good for keeping information organized, but they're also really helpful with probability. So in this video, we're going to look at some examples of tree diagrams and also how we can use them to calculate probabilities. Okay, so our first example, you get a job, yay! You have a signing bonus, which you get to use to buy a new couch because adulting is super fun. The couches that you're looking at can come in micro suede or leather, and then you have the color options of black, tan, green, or maroon. So we want to draw a tree diagram to represent your couch options. Remember, when we're drawing tree diagrams, we look at each aspect separately. So first, I'm going to draw the couch. And there's cushions on the couch, and there's little legs. And up here, there's a cushion. Oh, perfect. And first, we're going to look at the first aspect. So the first thing we have to decide, or we have the option of, is the material used. So we have micro suede or leather. The next thing we do is we then match each color option to each fabric option. So we could have micro suede in black, micro suede in tan, micro suede in green, micro suede in, I can't use maroon. We'll use an N for the end of maroon, right? I can't use the M because I already used M to represent micro suede. If I wanted to, maybe I change this. Now that I'm thinking about it, maybe it makes more sense for that to be an S for suede. And that way we can use the M for maroon. Okay, and then we have also leather could be in black, leather could be in tan, leather could be in green, or leather could be in maroon. So we see here that we have 8 possible options. We have micro suede in black, micro suede in tan, micro suede in green, micro suede in maroon, leather in black, leather in tan, leather in green, leather in maroon. So those would be in there, right? Make it much prettier. So we have 8 possible options. Oops, except I changed maroon to red. Oh, I see, because I didn't like the M. See? I'm always thinking ahead. Okay. But now, you go home and you tell your boo about your new job, yay! And the new couch. But then your boo decides, wait, do we want to consider getting a recliner? How does that change the number of options? Well, I'm not going to draw them all out because it's really hard to do, but here it is. So first we have the fabric. Then from the fabric, we have the color. Then from the color, we have to decide or look at the options of there being a recliner. I'll write that underneath, of whether there's a recliner or not. So we end up having a total of 16 very crowded options. So you can see the tree diagram is nice to display, and you just read it along the branches. So one couch option is micro suede in black with a recliner. Another one would be leather in tan without a recliner, and every possible option that we have. So it's nice. It can get crowded, so we do have to be careful about that. Okay, so as I mentioned, tree diagrams are especially useful for calculating probabilities of 2- or 3-part tasks. What we do is we put the probabilities on the branches of each event. So for example, if we want to calculate the probability of flipping 2 heads in a row. So the situation here is you have a coin, you flip it once, you record what it was, whether it was heads or tails, and then you flip it a second time. What's the probability that it's 2 heads? You might already know the answer to this, you might not, but we can use the tree diagram to set it up. So whether you do or don't, let's see what happens here. So here's my coin. There we go. And the first flip, we have the choice of either heads or tails. So this is the first flip. Now the second flip, we have to say, well, if the first flip was heads, the second one could be heads, or the second one could be tails. Or the first one could have been tails, and the second one could be heads, and the second one could be tails. So we see there are 4 possible options, right? We could flip heads then heads, heads then tails, tails then heads, tails then tails. What we do for the probabilities is along each branch, we put the probability. So the probability of flipping heads is 1/2. The probability of flipping tails is 1/2. And then over here, we do the same thing, but we just consider this. So the probability of flipping just a heads one single time is 1/2. The probability of flipping tails one single time is 1/2. We do the same thing down here. So the probability of flipping heads here is 1/2. The probability of flipping tails here is 1/2. Okay, so we have all these 1/2s everywhere, which is super adorable. But now, how do we decide what's the probability of the heads, which is listed right here? If we go along the branches, if our tree diagram is horizontal and we move horizontally, what we do, so we're looking for heads and then heads, we multiply the probabilities. So it would be the probability the first one is a heads times the probability that the second one is a heads, giving us a probability of 1/4 or 25%. So again, you might have already known that, you might not, but this is how we can use the tree diagram to help us. So the probability of heads then heads was 1/4, because as we go along, we multiply the probabilities, right? If you notice each branch that meets at a vertex, these should add up to 1, right? Because the probability of something happening is 100%. But as we move from here to here, that's where we want to multiply the probabilities. So there's a lot of different things going on with these tree diagrams. Last example. A bag contains 8 blue marbles, 4 red marbles, and 6 purple marbles. 2 marbles are drawn from the bag without replacement. And without replacement means that one is drawn and then it's not put back in the bag, so we no longer consider it. Then we have a bunch of things to consider for probabilities, and these can be really tricky. As you can see, the language can be very intricate here. So first, let's set up our bag. All right, so my bag is going to have a handle, and we have some blue marbles. I'm not going to draw them all. You get the idea that there's marbles in that bag. Okay, so the first draw, we have 3 possibilities, 3 possible outcomes, right? We could draw a blue, we could draw a red, we could draw a purple. Now what we want to do before we move on to the next set of branches, we want to put the probabilities of each one. Now the probabilities are not 1/3, 1/3, 1/3 because there's different numbers of colored marbles in the bag. So how many marbles are in the bag? Well, that would be 8 plus 4 plus 6. So there's 18 marbles in the bag. The number of blue is 8, so the probability of selecting a blue marble would be 8 out of 18. And we can simplify this or not. It doesn't matter. It's up to you, or you should ask your instructor. The probability of red would be 4 out of 18, and the probability of purple would be 6 out of 18. And again, going down these 3 branches, so 8 18ths plus 4 18ths plus 6 18ths, that should add up to 1, because there's a 100% chance that if you pick a marble, it's going to be one of those 3 colors. Here's where it can get a little bit tricky. Now, we say in this top branch that the first marble drawn was blue. That means now, if the first one was blue, there are only 7 blue marbles left in the bag, because we selected one and it said we didn't put that marble back. So now these branches get to be a little bit more complicated. If we draw a blue marble first, we still have the option of drawing a blue marble, a red marble, or a purple marble, but the probabilities are all going to be different. The probability now, so first there's 1 fewer marble, so there were 18, now there's only 17. There's also only 7 blue marbles if the first one was blue, so the probability that the second one is blue is 7 out of 17. I don't know why the screen's getting all funky. Sometimes it does that. Okay, so I'm going to put it over here because it's not working over there. So 7 out of 17. And that's strictly just looking at the fact that there's 1 fewer blue marble left in the bag, the probability that that second one is blue. The number of red, there's still 4 red marbles, so the red is going to be 4 out of 17, which maybe I can, oh good, it's letting me right over here. And there's still 6 purple marbles, so it's 6 out of 17. And again, these 3 that with this common vertex, these should add up to 1 whole. 7 plus 4 plus 6 should be 17. 17 17ths is 1 whole. Okay, so that's selecting a blue first. Or we could select a red first. If we select a red first, we still have the opportunity of selecting a blue, a red, or a purple marble second. But in this case, there's still only 17 marbles, just like there was when we selected a blue first. But now we're missing one of the reds. So the probability that a blue is selected second after a red was selected first, there were 8 in the bag out of 17. There's 1 fewer red, so the red there's only 3 out of 17. And purple, there are all the purples, so it would be 6. I'm running out of space here. 6 out of 17. And then last but not least, if a purple is selected first, we can still pick any of the 3 colors. We could pick a blue, we could pick a red, we could pick a purple. The second drawing, again, there's 17 marbles. And all the blues are present because we drew a purple first, so it'd be 8 out of 17. All the reds are present because we drew a purple first. There's 4 out of 17. One fewer purple, so there were 6, now there are only 5. So we would have 5 out of 17. So that's what this would look like. Very complicated. Review this, make sure it makes sense. When we look at each piece, we're looking at that current situation given this thing already occurred. Okay, so now we're going to use the tree diagram to help us answer some probability questions. You can see now, hopefully you can see now why this tree diagram is really nice, because it keeps things organized and it kind of like displays everything. Okay, so what is the probability that 2 blue marbles are selected? So that's going up here to blue and over here to blue. So the probability of blue, then blue. Since we're going across horizontally, we're going to multiply. So that'd be 8 out of 18 times 7 out of 17. There's not a whole lot of simplifying that can happen. In fact, all we can do is simplify this. And so we'd end up with 28 over 9 times 17 is 153. If you can leave your answer as a fraction, leave your answer as a fraction. If you need to convert it to a percent or a decimal, the decimal would be 0.183 or 18.3%. So we could say that's roughly 0.183, which is roughly 18.3%. So almost, 1 in 5 times you're going to draw 2 blue marbles, which is kind of a lot, given that there's so many different possibilities, right? There's 9 different possibilities, and one of them is almost 20%. So that's pretty crazy. Okay, so this was A. B, what is the probability that a red is drawn first and a purple is drawn second? So order does matter here, right? Because we are specifying red first, purple second. So this would be the probability of red, then purple. And that would be, so we're going to go in the middle here, that would be 4 out of 18 times, and then purple would be 6 out of 17. And so that would give us, let's see, we could do this 1, this 3, and we end up with 4 out of 51. This one looks way less likely than the first one, doesn't it? So 4 out of 51, which is 0.0784, or approximately 7.84%. So much less likely that you're going to draw a red than a purple versus a blue than a blue. And lastly, what is the probability that a purple is drawn first and a blue is drawn second? So we want probability purple, then blue. So we'd be going down here. Purple, probability the first one's purple is 6 out of 18. Then we go across times 8 out of 17. So this would be 1 and this would be 3. And we end up with 8 out of 51. So twice as likely as red than purple. And if we convert this to a decimal, we would get 0.157 or 15.7%. So these are just some applications of using tree diagrams. As you can see, it's really helpful with probabilities. I know it can be very complicated, but we have to think about what the question is asking and then use the information in the tree diagram to help us figure out how we can correctly answer that question. Thank you for stopping by.